So, let us start lecture 14. The course is on phase diagrams in single component and binary systems, and today we will start looking at phase equilibria now, and now we will try to introduce one more interesting parameter which is called chemical potential. Till now what we have seen that we have understood equilibrium, and while understanding equilibrium we have left aside internal energy as well as entropy consideration for equilibrium understanding, and we have moved towards auxiliary functions. And in that auxiliary functions we started with Helmholtz free energy, where it is actually dependent on two independent parameters, one is volume, another one is temperature, and the second case which is Gibbs free energy, which is G, where we have taken pressure and temperature to be our independent variables. Now, while considering that, we saw that minimization in A as well as G, that talks about equilibrium, and while doing that we considered a closed system and fixed composition. But there could be systems where it will be closed, but there could be reactions, and when reactions happen then composition will not remain fixed, composition would change. Similarly, let us say we take open system, then in case of open system there could be exchange of matters with the surrounding, and then there could be addition or removal of molecules or atoms from the system in and out. Okay. So, those conditions we have to talk about size of the system, size in the form of number of moles, and that would cover up, that will cover also the composition change as well as the matter exchange with the surrounding, both closed as well as open. Now, so that time we have to bring in one more variable which is number of moles. Now, if we see that number of moles is also very easy to quantify, easy to control. Okay. And now we are left with three variables: pressure, temperature, number of atoms or number of moles, or volume, temperature or number of moles. And in the last lecture we considered that now onwards we will talk about every equilibrium in the form of Gibbs free energy, because most of our situations what we will be considering in our phase equilibria or the phase diagrams will be considering pressure to be most of the time pressure will be constant. Okay. So, now let us look into those variables again. So, the today's lecture would be the phase, we will now get into the phase equilibria part also, the phase equilibria and consideration of chemical potential. Now, we see that closed system and reactive system, open system. So, those two cases G would be function of P, T as well as N. Let us say there are ith component, number of components 1, 2, 3, 4 till ith component, okay, those number of moles. Now, if we see the variables, what are the variables? P, V, oops, this should be T, P, V, T, N. All those cases we will consider only this, this and this, because these three will be related to G. And in fact, if I try to compare the easiness of control of these four parameters, this is easy, this is easy, this is easy, but this volume is bit difficult if it is irregular volume. Measurement becomes difficult, okay, but still it is much easier than taking entropy or internal energy as variables. So, if I take this G equal to function of P t as well as N I, and the system contains the components 1, 2, 3 and ith component, these are actually variables or independent variables. And this part, the number of moles, will be considering the composition change as well as exchange between the exchange with the surrounding. So, if I consider this, still we know that equilibrium happens when G goes to minimum. Equilibrium is basically G goes to minimum. We have to find conditions for that when this one is also taken into picture. So, in order to do that, we will go systematically, and in order to do that we have to just derive few equations from this. So, I can write delta G equal to, so let me just write all those expression in the form of partials. So, like this I can write to okay, I can write this. Now, if I consider pressure and temperature to be constant, in fact, this part if I look at, this part comes out to be dG equal to, this is V dP minus S dt. Okay. And this is valid for closed system and fixed composition, and the equilibrium happens when GPT goes to minimum. Okay. So, now if I consider PT to be constant, delta G would be equal to all the other components are fixed, only there is a change with component 1. Okay. And interestingly, this one is nothing but is defined as mu I or G I partial. So, this is basically chemical potential, is defined as chemical potential free energy. Okay. Now, chemical potential, so I can write this from equal to mu 1 d n 1 mu 2 dN2 like this. Okay. Now, let us understand this chemical potential term. This is defined as chemical potential. So, chemical potential let me consider only mu. So, this is basically the rate of change in G with the change in ith component by 1 mole. Okay. So, this N1, N2, N3 are basically all the moles of all the components. Now, when I see this part, this particular part, this equation, in fact, this is also there is another condition, which is I am considering homogeneous system. Okay. Let us say in a system we have only one phase, we can consider to be like this. So, this is a homogeneous system, or I can say homogeneous phase. So, now this is for a phase, let us say alpha. So, that means correspondingly everything would be for alpha, that is for homogeneous phase. And this chemical potential is the rate of change of G of alpha, that is the alpha phase, with the change in ith component by 1 mole. Okay. Now, there is a condition. So, now condition is the size of the system is so large that this small addition of 1 mole or taking away 1 mole, it will not change the composition of the system. Okay. So, that is the assumption we are taking. So, that means here system is large enough so that there is no change in composition. Okay. So, this should be taken in mind. So, this is the rate of change of the system free energy with the change in ith component by 1 mole, that is the chemical potential. When we have that, the other components are fixed, no change in that. So, this chemical potential is then becoming it is basically for the component, and remember this is not, it is not for the phase. This is very important statement. So, now if I try to write a chemical potential of a component in a phase beta, I can write chemical potential of component I in phase beta. The beta would be kept as the superscript and I is kept as a subscript. Okay. So, that would be, how do we express chemical potential of ith component in homogeneous phase beta. Now, let us treat this equation again, and remember this time pressure and temperature I am keeping constant, and then only I can relate it to free energy. So, if I keep pressure and temperature constant, so that means this minimization of G would be decided by how we relate the chemical potential of different components in different phases. So, the equilibrium from this equation I can write the G goes to minimum, okay, and it will be decided by, since it is PT, by the relation between chemical potential of components in the system. And while doing that, now we are bringing in, since we are talking about chemical potential, we have to bring in multiphase. So, in fact, in system consisting of multiphase, okay, because we are talking about the size now. So, we can also revise this statement as it will be the minimization of G would be decided by the relation between chemical potential of components in different homogeneous phases in the system. What will be the relation? That will be our purpose in the subsequent lectures. So, we need to see that. So, before I go to those situations, so this how minimization would take place. So, let us deal with this equation again. So, I can write delta G, let us consider P and T constant, so that we do not mention it here. In this case PT, let us not write that, since we are taking PT as constant. So, it will be equal to mu 1 dN1 plus mu 2 dN2 plus mu 3 dN3 like this, plus mu I dNi. Now, let us consider that there is a small fraction of change in all the components in that phase. Okay. So, if I consider, and also it is for a homogeneous phase. So, del x is the small fraction change in all the component molecules, moles or component moles. Okay. If I do that, then dN1 would be definitely del x N1, N1 into del x. And why we could do that? Because N1, if you see, it's a number of moles. So, the number of moles, if we have, let us say 1 mole, 2 mole of a single component, we can see what will be the total mole is at 3 mole, 1 and 2 moles. Okay. So, it is basically additive. So, it is a kind of again extensive property, just like free energy G, which is also extensive property. So, this one, this dN2 equal to N2 del x, dN3 equal to N3 del x, like this. dNi would be equal to Ni del x, and N1, N2, N3, N4, those are basically number of moles of different components. Okay. Please understand that 1, 2, 3, 4 are not the number of moles, rather number of the moles of those components. And G is also extensive property, just like number of moles. So, then I can also write del x G would be equal to delta G. So, I can write delta G equal to del x G del x equal to mu 1 N1 del x plus mu 2 N2 del x like this, plus Ni del x mu y. And if the change is additive, we have to consider additive. If it is subtractive, it should be subtractive. Okay. So, then I can write this one as G equal to mu 1 n 1 plus mu 2 n 2 plus mu y n I, and this is for a particular phase, pressure and temperature constant. So, this will be also for a particular phase, homogeneous phase. Okay. Please, this is a very interesting equation, and these equation will be considering while coming to the relation set up between chemical potential of a component in different phase. So, from here also we can treat this equation again. So, I can write delta G equal to mu I d mu I d n I plus n I du mu I plus no, this is 1, 2, 3 for all the components. Let us consider 1, 1 plus mu 2 dn2 plus n2 d mu 2, like this. I can go up to ith component. This is the system has that ith component, n mu I dni plus ni d mu y. I know that delta G P T, it is constant pressure and temperature, same phase, would be equal to we have proven this before. So, then I can write this one as n 1 1 plus n 2 d mu 2 plus n 3 should be equal to 0. So, now we have couple of interesting equations. So, this is one, let me mark it with color. This is another and this is another. So, these three equations are called Gibbs-Duhem equations. Interestingly, these equations will be used while deciding the phase equilibria between different phases in a system. Okay. So, these will be very useful, that is what we have derived these three equations. So, we would like to understand physically that what is the meaning of mu, okay, which is the chemical potential or partial molar quantity of a particular component in a phase. Fine. So, that will be decided by a consideration of escaping tendency of a molecule leaving one phase to another phase. So, in order to understand that, we have to take reference of some other variables like temperature and pressure, and if we understand the temperature and pressure also will be related to escaping tendency. For example, temperature would be related to the escaping tendency of heat and pressure would be related to the escaping tendency of molecules from a system to another system. So, we will try to understand that physical significance of mu in our next lecture. So, till then, thank you very much.